Yeah, no. So the point of all this is just to get everybody comfortable with C++, classes, member functions, private data, and public data. So now that we're all programming experts.
And what we really should do is instead of returning 4, we should actually throw an exception.
No.
Like a jerk, like if you're a jerk exception.
Yeah, right.
That way the information can get carried all the way down to the main call.
Okay, so
Unless they hate your jerk.
have it written into the ROM memory addresses. Okay, so has everybody that wants the code from that link downloaded it? Okay, so now we're gonna.
Now, like immediately.
Huh?
Can you like do it immediately, like right now?
What? Do what?
All of that.
All of that? Okay, I'll do all of that. So
Too late.
we've got a couple of functions in this, a couple of scripts in this function, in this solution. So we've got a controller H, a controller CPP, we've got a moving average H, and we've got a moving average CPP. So what we're going to do, I'm going to start with controller H and just talk about what's going on here for a little bit. Now, I've seen different people code differently where they just already know, like they could sit here right next to me and just write their member function without thinking about it. For me, I'm not there yet, so I'm going back and forth where I'll do some developing and then add a couple of functions to my class as I go and kind of go in between there. But it's a good idea to start. If you can start with laying out, well, what does my function have to do? It's a good place to be.
You know exactly what member functions you're using C. None.
None. That's right. So, but we're going to have. So we're going to have the constructor. We're going to have your destructor. Now, I'm a big fan of passing in variables at runtime, and this is something that ROS is spectacular at. You literally call it. It's a ROS param. You make a text file. There's one line of code, 4 if you want error checking, and it's just going to read that in at runtime. There's no if streams or of streams or any of this other insanity. But it's the point of having variables that you can update at runtime is that you don't have to recompile your program if you want to change the value of something. And it's something that, especially when you're testing and you're debugging, you don't have to recompile every time that you change a 1 to a 2 or a 2 to a 3, or you're testing strings or whatever like that. So this getParams function is built to, now let's go and check that out. So this is close to what reading in from external file looks like in C++. I say close because at this point of the code, my state variables hold. Like the value that I want is in this mode, this dot mode, and in this dot tolerance. But for whatever reason, in the time before this, I couldn't get it to remain there.
Your error handler isn't very insulting.
Yeah. But so what's going on here? Let's look at this, right? So I have mode and tolerance reader. So for in my code, in the PID controller, I want to be able to set the mode, meaning if it's user-defined inputs, if the script is in debugging mode, or if it's in autonomous. And the reason for that is development. Is when I'm just behind the lab in the pool, I want to be able to send it 20. I want to go on a compass heading of 20 and make sure that the vehicle is pointing in the right direction. But later on, once things get a little bit more advanced, I'm going to be updating that desired heading via an autonomy command. So it's cool to be able to have multiple options for your code. And debug is good too because while you're going through development, you're going to have all of these print statements and all of these different warnings and insults that you're going to have your computer tell you. And I don't know whether it's just nostalgia, but I can never quite bring myself to just delete all of them after I've developed the code. So I'll keep some of them. I mean, I'll delete a good bit, but sometimes I might want to know what my motor commands are to my thrusters, but other times I don't really care. If it's running, then good, it's running, and that's enough for me. So those are my three go-tos for modes. Again, it's user input, autonomous, and debug. So now this mode intolerance reader, what do we think? Is it going to be public or private? Public or private?
Private.
Did Travis do his job? Oh, and there it is. It's right inside that private data, private. And this is a pointer so that I can dynamically allocate it. I can make this one.
Probably make it protected though, because if you inherit the class,
We'll be talking about that in 2 weeks from now. Actually, we probably won't be. I don't know what's in 2 weeks. But, yeah. I appreciate it.
I was in on the ass.
Yeah.
You just said like 5 seconds later.
So, let me just shake off my shame. And, okay, so, yeah, thanks.
Put your head down and shame.
That's right. So you can see now we have this mode intolerance reader, and I'm dynamically allocating it, and it's a new ifstream object. And ifstream is your input file stream. Pretty much it's what allows you to read in from a text file like you might find in your solution. So Visual Studio likes to obfuscate where their stuff is, and it's always kind of a, I guess this wasn't that big of a pain in the neck, but compared to other things. Yeah. So I have this text file here, and the other thing that's also watch out for is depending on how you make your data file. I've run into the issue where sometimes I'll have like .txt on the end, and what's actually going on here is that .txt extension is twice in the actual call of like the actual name of this file.
and then you can change that in Windows. Like,
Yeah.
Windows by default.
You go, actually, if you go up to,
Okay, point is,
home up there.
watch out for it.
Or, no, it's not home.
So you can definitely change that. I'm sure that you can. Point is though that just watch out if you haven't changed it.
Also, like, you probably want to make that like a custom extension.
Usually it's like, if it's like.
Dot data, sure. You could do dot dat.
Well, that's usually binary data. Usually just do .cfg or something like configuration stuff.
Okay, so
That's usually binary.
you could, and honestly, you could call it dot Travis
Yeah.
whenever you want.
There
So
but there's already such file as that.
is there?
There is already a type.
Must be the best type there is. So just for right now, it's gonna be the .txt though, and
There's also already .davis.
what it allows you to do is, so this if stream has a whole bunch of member functions, and it's going to read in. If it's not good, it's going to let you know bad file, and it's going to just go through until the end of file. And
I got a question.
yeah,
Why are you using a char array instead of string for this temp mode?
yeah,
Char arrays are awesome.
yeah. Well, no, because I was not. So 2 reasons. One, I developed this in like 30 minutes, and 2, because I tried doing it that way, and don't you have to use string streams
I don't know.
then? Because I don't think that you can actually, get line,
Get line.
because it's
Get
so
line
the
only takes a char array.
yeah the get line function. No, it might actually. Yeah, it is. I think, but I
Maybe
think
it was a get, oh.
let me
Just
see.
Go ahead and get line, type parentheses, and hit control space. It'll give you all the options.
That's also part of it though. It is overloaded for strings, but it starts throwing errors when I'm using this pointer for this, and even without it, because
Mode is a pointer itself, isn't it? No.
no, it's not. So yeah, if it was up to me, I wouldn't be doing it this way. I'd be doing it in Linux and ROS. So
Use string.
this is also not a fully debugged function, but this is along the lines of what you want to do. You've got your function, you got your if stream, you're going to get a line, and for me, I'm going to use the whole. Now, you can also do parsing and things of that nature, where if you have multiple variables on the same line, but my config file has 2 lines, and there's one thing on each line.
Brushes and stuff, you can do like in the string queue,
That's pretty cool.
so you don't need any of that stuff. Just use random expression.
So now that we have our mode, and we also have this tolerance. So this,
You don't have types.
you'll see here I have this variable called tolerance declared. And, the Marine Robotics Club is just a tolerant place. It takes many kinds. So now the point is this is kind of,
Tolerance equals 0.
yeah. So back when we were talking about the response of the system, you're never going to have 0 compass error in the real world. You're not going to have 6 decimals of 0 precision. So it gives you a little bit of a wiggle room where maybe plus or minus 3 is enough, or maybe it's 1 degree. And
0.01.
yeah, 0.01. But whatever you want to set your tolerance, what this tolerance is going to do is be kind of a bounding box for our system response, where it's going to be when we turn off the PID controller. Because the whole point is that, all right, I want to go this way, but I'm pointed this way, so I have to turn. Well, when do I stop turning? When I'm within this tolerance. So now that I came within my margin of error, now I'm just going to go ahead on that straight line. So now we have our mode, we have our tolerance. So those are the two primary things. Now, the other aspects of the controller are your desired heading, your current heading, and your motor speed, and your gain. So those are 4 more variables that you're going to want to have there. And if we come down here, so I think I actually can make these private. Yeah. So if you downloaded that code online, I did not move over actual heading, filtered heading, and heading error into private data, but you can do that. I got that going before the seminar. So, all right, so the heading gain, where do we get that from, right? So there's a KP, there's a KI, and there's a KD. And you can use MATLAB for it. You can do numerical analysis. There's a bunch of different ways that you can get it. There's also ways that you pretty much kind of put your system, make your system run, and you set your gains up to the point where your system is unstable, meaning you crank them up as high as they can go, or even higher, like 10,000, whatever it is, and then you slowly start stepping down with a ratio of 2 to 1 of your P term and your D term to your I term. And again, that's because your I term is going to be a lot bigger than your P and your D. So there's a bunch of different regimes for how to go about getting those values. But in this setting, all that we're concerned about is...
The best way to do it is to just give it to Travis to do.
Yeah, thanks.
Use somebody else.
Yeah, you just give it to somebody else. So now I have this function, and this is, again, so I'm just moving down my header file and saying what the function, the member functions are in here, and then moving to the code. And this is kind of the way that I thought through this code. So we have this mode-specific setup. So now if we have these 3 different modes that we're running, well, we're going to have setup that's specific to each one of those. For example, if we're doing a user input, what you really would be doing here is reading these values in from some external file. Would be the whole point, what we were talking about, so that you don't have to recompile every time you want to change it. That's when that really comes in handy. Let's say I just want to test out my motor at different speeds. Well, now I can send it, 10%, 20%, 50%, 100%. I didn't do that with this. I just hard-coded it in, but you get the idea. This is about controls, not about C++ programming. So again, though, if you have access to ROS, if you're developing some sort of system, highly suggest using Linux, using ROS. Those two tools in conjunction are ultra powerful.
Use Qt also.
Yeah.
Does Ross do this control alright?
Controls,
Like PID loops?
Yeah, it does, actually.
ROS does? Okay. Nice. Seminar over. Look up the ROS tutorials.
There's also a QPID,
Okay.
I believe.
Yeah.
Is it really?
I think so. There might be.
You just made that up, Harold. Bogus. You're making up lies. So, we have the forward heading gain, we have our desired heading, and the constant motor power. So this is just a heading controller. Now, the vehicle needs to operate at some speed, some velocity, which is the heading and the speed. So you could implement a controller that closes the loop on both of those. That's not what this is. This is just a straight up, in fact, right now it's just a P. We're going to work on implementing the I and the D by the end of this seminar. But yeah, you need to give it some reference point where you just say, all right, go ahead at 50%, where this 50 is a percentage of whatever motor power you have access to.
That means your PID loop's gonna try to stay at 50% motor power?
So the PID is going to. So the PID isn't about motor power. It's about the error in the heading. So it's going to set off. It's going to output a signal. Yeah. So it is going to output a signal to your motors. It's going to be an RPM signal. But that signal is what gets scaled by this. And this, because also, especially for this implementation, is for a differential thrust boat. So when you're turning, that time is really fast. So whether you're at 100%, 50%, 10%, it's still going to be pretty quick no matter what that value is. The constant motor percentage, damn. Okay, so the constant motor power is more for after you achieve your desired heading. So now that I've spun and I've gone and I'm pointing the direction that I want to go in, well, how fast am I going to go along that line? And that's what this constant motor power is more for. It sets that value equal to 50%. And again, you would have your routines here where for autonomous, if you want to listen to some high-level system, you would have the code there to do so, and the debug. This is just setup for it. So the reason why we are just declaring these values here is so that the code doesn't get hung up, because other parts of the code are going to want there to be a value there, and if there's not one, it won't continue. So now fill buffer. So now let's talk about a moving average filter. So in sensors, you're going to have this high frequency noise, this high frequency response, and you're not going to have an instantaneous change from a 300 degree compass heading to a 330 degree compass heading. It's just not going to happen. So what you want to do, now we're talking about the frequency. So this is a low pass filter, because when I've got every time
Fail.
Do whatever you get.
Smash with
slam dunk it,
Hey!
Kobe. That one's not strawberry. There we go. I got my cherry marker. So yeah, it's a cherry scented marker.
Is it really?
Yes. I'll pass it around afterwards. So now I've got my compass. Like, I'm getting data from my sensor. And really what you would expect it to look like, is something pretty straight like
That looks
that.
awful.
Yeah, actually it's not going to prove my point. So let's say that I'm spinning in a circle. I'm just going from, just spinning in a circle. So it's gonna actually, what's it gonna do? It's gonna go up to 360, and then it's gonna drop to 0, and then it's gonna climb back up, and it's gonna drop to
Well,
0, and it's gonna
Yeah, it's
climb
gonna
back
be
up.
like, it's gonna be a sawtooth.
Yeah.
Like that.
So now that's what you would expect it to look like, but really what it's gonna look like is there's gonna be all of these little jumps up and down where, it's a hiccup in the line, there's some electromagnetic response so that corrupts your signal a little bit, and it's just some noise, right? There's some noise in the system. So we have a couple of different signals here now. So now, not only do we have, now if we look at the frequency response, not only do we have this one main signal, right? So it's pretty steady, so that's gonna have a pretty low frequency. But now this is moving rapidly. So every single one of these jumps is like a very high frequency sinusoidal signal. So you're gonna have all of these this high frequency scatter in your system. So, the moving average filter, it pretty much, what it does is it takes your past,
But you do want those high frequency transients where it goes from like
yeah,
that vertical line.
definitely.
So you have to like know if it was because of that or not as well.
Yeah.
'Cause
But
otherwise
also-
they'll filter that out and you don't want to do that.
If you're really going,
Because
Yeah.
you want it to wrap around like immediately, like once you get 360 back down to 0, you want that to wrap around immediately.
but that's also why you have the tolerance.
Mhm.
So because if you're plus or minus on
Yeah.
there, then you're good, and it is good coding to, yeah, I mean, that is a good point, where the moving average filter, the size of it is gonna be what dictates your cutoff frequency. And good engineering would mean that you figure out what the frequency is of that drop, but also,
What a more elegant way of doing it would be to not drop off, but to keep going in the average. Like okay, we can't just start adding in zeros now because that's going to 12 hours. But go ahead and add like 362.
yeah,
So that way you stay within
to get there.
the average.
Yeah, but the,
Just a bit of logic in the filter. That's all you need there.
so there are more advanced filters than a moving average filter.
No, there'd still be moving averages. Have to have extra logic in them just to figure out
Yeah,
to continue whether or not to reset the 0 or keep going up.
yeah,
Because it's going to reset the 0. It's going to wrap around anyways once you put it into the actual set heading.
yeah.
And you give it 362, it's going to wrap you too.
Yeah. More than one way to skin a cat. So,
Then
the
you
point
wouldn't have to
is,
then you wouldn't have to worry about transient being filtered out.
yeah. The point though is that now what you're gonna have is this response where you are having some phase signal. And it's probably not gonna be as dramatic as that, but what this is doing is it's cutting off all of this high frequency noise, except you can, cutting off that high frequency noise, but it does mean that you have a phase shift. That is, it's inherent to a moving average filter, because what it's doing is it's literally taking the last 20 readings and weighing them, so that every time that I get a new reading, it's averaged with the previous 20. So if I do have this big update, where if I am turning sharply, it's going to take 20 samples at that new heading until it's thoroughly updated. So it's there's a trade-off here. You have to find out what the right value is. If you make your buffer too large, well, then you're never going to update. You're going to have hours of delay, and if you don't make it enough, then you do have just this jumping back and forth of your signal. So this buffer now is actually, so let's look at this code. So I come down to my fill buffer, and there's this object called the heading. So the heading. So what is this? Well, if I come back to the controller.h file and I scroll down to my private data, The private, yeah. So I have this moving average class, which is the other aspect of this solution. So now I'm going to look at this moving average. So now this is another class that's specifically a moving average filter. So it's got a couple, it's got your constructor, your destructor, an add heading, print, buffer is full, get filtered heading, and the buffer size. And this buffer size now, you can change that in your program. Let's say you enter a regime of the course where,
Plus buffer,
yeah, the buffer.
and then.
So
and
if-
then make this a frame plus buffer. So like buffer has all the mutators and.
So
So what is buffer?
So the buffer is the number of readings in the moving average filter.
Okay.
Yeah.
What is it, a vector or is it a what?
Just an int.
It's just an
Yeah, you should
Yeah.
make another class buffer that had its own like mutators and.
So how do you put your values into that buffer? If it's just one int?
So this is just the size of the buffer.
Right.
The actual buffer is a float pointer.
Okay.
Yeah.
Vector
So,
or float?
so,
Why don't I make it a vector or float?
Yeah, vector float's probably better.
Float star is so C, like, why are you in the C way?
because I felt like it, people. Yeah, I mean, vectors are more elegant. This was also, a lot of this code this wasn't purely developed in C++. It was ported from C. So there were some parts of the code that I'm not the original author of this, I'm the updating author. So there's some parts of it that have been updated, there's some parts that haven't. So, so in my constructor, I set the buffer size equal to 100, and then I go ahead and I create this heading buffer with a size of 100, so it's 100 floats long. Now, destructor is going to delete, and my moving average. So now, if I want to add a heading, so let's talk about this logic. What this does is, because we want to, the whole point is that it's moving. So as I get a new reading, I need to add that new reading and also take out the last reading.
Yeah, you gotta pop location 0, you gotta append the new one.
Yeah, so you gotta pop and push. And I guess, yeah, this actually would be a lot easier with the vector because you could just pop and push.
If you had a float pointer, or if you had like an index of your current position, and just up, that way you keep the float array, you don't have to move anything around it, you just have the index of where your current position is. And just overwrite that one, and then do the previous index and overwrite and remove that one. So that way you won't have to ever shipping around the array, you just using two indexes.
Or you just use vector.
Yeah, the vector, because that also has indexes.
Yeah.
You can literally use
Yeah,
uh,
this also works. So,
Size -1, -I, -1.
yeah.
Can we just say -2?
Yes, you could do that, but I'm also a big fan of logically readable code. So for me, it's one back from this other one. So-
now you gotta move shift every single thing.
We can do the code review on Saturday. For the purpose of this works, and I'm presenting it. There are myriad ways of implementing moving average filters and many other things across the coding world. If you want, Harold, you can download this code and just
I'll fix it.
skewer it whenever you want. Good. See? Give it to somebody else. Like you said. If you want something done, give it to somebody else. Harold, fix the code. So, what this does though is it
It's not boring.
it also
It's not used for anything else.
it loads it from the back end because right if it's buffer size -1 -I. Yeah, so this loads it from the back end. And what it allows for is actually, what am I doing Yeah, so that way I don't have to keep track of the index, because what it does is it's always adding to the first position in the code, and then it just pops out the back.
You know, what you'd do is you'd have the average plus the element at the current index minus element at the index minus 1. Using mod as a arithmetic, of course, make sure it doesn't, so that it wraps around, but
Yeah.
that's all it'd be. And then you wouldn't have to shift anything around the array. You'd just be updating using the index, using the pointer into the array. So that's how you're supposed to handle arrays. Even with vectors, you have indexes into the vector.
Yeah, I mean, this is what the index is.
Yeah.
This
But
is the
you're
index.
basically shifting all the numbers around the array constantly. You shouldn't have to do that. You should be able to just access them directly, like just move your index around. So rather than having a hard code as heading buffer 0, that'd be a heading buffer index position.
Yeah, but there's two different cases. So there's the initial case when you're filling it, and you have to be able to access all 100 positions.
Yeah.
And then you also have the transient case or the steady state case, when you only need to access the first position.
Yeah, but the index will still handle that because if you don't have them all in there, your index starts at 0.
Yeah.
So you just add, you
Point of
just,
assembly.
So, again, thanks, Harold. Point is, are we all clear on what a moving average filter is?
choose that.
Yeah. Okay, cool. So we have this moving average filter, and that's going to damp the error, the noise of the controller. So now let's look at the constructor. So we've gotten through a couple of our core functions here. We've gotten through getting the parameters for what mode you want to be running in. We've gotten through the specific setup that you're going to do for each one of your modes, and we're going to go into the filling of the buffer. We talked about those. And all of those are going to be done every time that you call another controller object. So it's a good spot for them to go is in the constructor. So now when we go to the source, all that we have is this constructor, controller PID, and it automatically gets your parameters, it sets the mode, and it fills up your buffer for your moving average filter. Now, little debug statement, that if it's debug, it's going to print out what the heading is. So let's go into, now in the matter of time, and because my computer just yelled at me that it's got 10% battery left, we're going to go through the rest of this a little bit quicker.
Like immediately.
No. I mean, 10% still pretty good. Still got 30 minutes left. Golden. So we declare that controller, and it fills up all the variables like we spoke about before, and then we're going to enter our main loop. So our while loop, if you will, the mega loop. So you'll see here now that all of the operations that are being done are all being done by member functions. I'm checking flags, I'm adding headings, I'm setting headings, setting and getting the heading error, print heading info. So what you've got here is this flag check. So you want to make sure that your compass or whatever your sensor is actually got a reading before entering your control code, because depending on what type of message passing regime you're going with, ROS, LCM, serial, whatever control regime you're using, you have a chance of not having a message in your variable. So you want to make sure that you're always working with the most recent version. The reason for that is because the timing of your program might line up with the timing of the message that's getting passed in. So if this goes and if it's not getting that message at the right time, well, then maybe there's not that message there. So that's why you want to make sure that you check your flags, which are, if we go back to the controller.h, we have our compass flag and our command flag. And if we go to controller.cpp, we can see, you do a search for check flags. So if compass flag is equal to 1 and command flag is equal to 1, this will equal to true. So this is another just little error checking built into a function call. So every time that this loop goes through also, you want to add a heading into, so this add heading function is, it just takes, so you would actually want to get what your new heading is. I just have it hard coded to 30, but that's where you're going to call your sensor, or you're going to, listen to your sensor and get the most recent heading and put that in to the moving average filter. So you're going to take that heading and put it into your moving average filter. Later, Sam. Yeah. So then you want to set and get. This is a double whammy. Your set and get heading error. This takes the just desired minus your filtered, right? It's what you want your heading to be minus what your actual heading is what gets set for your heading error. And then just a little print statement where this is going to print. Now, all of these are all member functions because all of the variables that they're changing are all private data. It's all state variable. It's my heading. So I want to make sure that that's not being changed by anything except functions that I wrote, or that you wrote when the time comes. Now, the fun part, the best command. So it's the PID controller dot heading controller. So now we can go into the heading controller because we have our actual heading. It's been filtered. We have our desired heading. We have the motor speed that we want to go at. We have our input mode. We have our tolerance. We have all of these items. So now what we're going to do is actually send, we're going to find out what the thrust commands need to be, because that's the way that you control heading on a boat, is you're actually going to have to send out a thrust command to each one of your motors so that they get to the right spot. So now you'll see here, if I've got a couple of different cases, So if the heading error is less than the tolerance, now you'll also see here like this 100 divided by 180. This is legacy code where I guess they did some testing on what that scalar should have been, and that's dependent on the model of the vehicle. So if the heading error is greater than my tolerance, so that means I'm outside of the bounds of where I want to be. So I've got my heading error, and I am actually subtracting the tolerance from it. So that way, minus tolerance. Honestly, I wouldn't even really do that. This is legacy code again, so forgive me. Let's say, all right, for right now, forget this tolerance. There could be something that I'm forgetting about it. I don't think so. Because really all that a P term is it's your P gain times your error. So this whole tolerance thing doesn't really come into play for this. It's garbage. So it's your heading error times your gain. Now we also have plus this constant motor power. And the reason for that is that way we bump up the response depending upon that motor input. So this is actually, it does come into play, where now if let's think about this for a second. So our heading gain is really big, or pardon me, our heading error is really big. Yeah, it's a really big number. We're way off from where we want to be. Well, we're pretty much going to have saturation of our system. So we're going to be running, if this is 10,000, our bounds are going to be somewhere. Yeah, so it's 180 degrees.
Like an offset, like a DC offset, and then you just subtract your add power to that.
Say that again?
Like your constant motor power.
Yeah.
Like your offset, right?
Yeah.
Your constant term.
So what you're going to have though is that now when you are, so we have this large error, so we're going to have this large response. but as that error gets smaller, we still want to be snappy. Like it's because otherwise, if we didn't have this constant motor power, we'll never achieve the goal because the error is going to be getting smaller and smaller, which is going to make our response smaller and smaller and smaller. Yeah. So we want to have that constant motor power there so that no matter what, we're going to be moving towards our goal. And if it's the sign conventions on this. Yeah, so now what do we want to do? If our heading error is greater than our tolerance, so that means we need to turn. And we want to make sure that we're turning as fast as possible. So because this is differential thrust, if we're moving our port thruster, let's see, if it's, this is actually going to be turning us left. So, yeah, so our starboard here is positive. So that means that this is moving forward. So what we want to do is also move the starboard, or pardon me, move the port thrust backwards so that we're spinning at maximum effectiveness. As fast forward as we're moving with our starboard thruster, we're going in reverse with our port thruster. It's pretty much the same deal. It's just negative heading error plus this scalar times the forward heading gain plus that constant motor power. And if the heading error is less than the negative of the tolerance, it's going to spin in the other direction. And finally, if the heading error is greater than, if it's less
That's
than,
within tolerance there.
yeah,
Travis, you need to save your recording so, because if it hibernates.
Right.
Yeah, you're done.
all right, so we're back on this now, and so we've got that if our heading error is above a certain value, we're going to turn left. If our heading error is below a certain value, we're going to turn right. And if our heading error is within our tolerance, right? If it's greater than negative tolerance and if it's less than tolerance, well, that's where we want to be. So at that point, we're just going to output that constant motor power. We've achieved our objective. And now it just gets piped into this 2-channel array. We also want to check for saturation functions, where this motor power is scaled to be negative 100 to 100. So that way it's just very human readable. 100 is full forward, negative 100 is full backwards. But if my heading gain, for example,
You can just use the min-max functions and just set motor power equal to like the max between motor power and
yeah,
or the minimum. That's a bit more readable.
yeah, for sure.
That's good. Yeah. Who cares?
So yeah, I mean, you're right. Honestly, this is a separate operation, so it should be a separate function, right? Like in a perfectly coded program, no function really does more
Really,
than
that
one
actually
thing.
should be a private function.
Yeah,
You just shouldn't be able to do that externally.
yeah, sure. So, but the idea is that you want to have a saturation
Actually,
function.
it's a protected function.
Yeah.
You don't really inherit it as well.
So if I look now at this power starboard, not starboard. So I've got 5/9 times the heading error times this forward heading gain plus this constant motor power. I can very easily have a motor command that's more than 100, which is going to be outside of the bounds of what I can send my thrusters. So all this does, it's a clip function where if it's above or below 100 or negative 100 respectively, it just sets it to what your maximum values can be. Now, this next part, the set dec motor command, is setting the decimal motor command, where this is a result of writing output to PWM. So you have, depending on what thrusters you use, you're probably going to be sending them PWM signals, which is pulse width modulation. And what this does is it scales the output that I'm sending from negative 100 to 100 to the band of your PWM channel. Let's go really briefly into it. Okay, sticking around. So
Let's do it on the whole. Way overshoot there. You should retune the PID.
yeah, I know, right? I need to bump up
Yeah,
my gains
way
a little
to his
bit.
peak.
Yeah. Okay. So yeah, pulse width modulation. So pretty much what your signal is going to look like, right? You're going to have a couple of different possibilities. Where let's say, for example, you have 1900, 1500, and 1100. So what's actually going on here is that you're sending, if you're sending full reverse, you'll be sending an 1100 millisecond pulse width. So it's going to look like that. If you're going 0, you're going to send it a 1500 millisecond, and if you're sending it full forward, you're going to be sending it 1900. So what this function does, this set deck motor command, is it converts that negative 100 to the negative 100 to 100 into 1100 to 1900. So it's going to set it on that scale.
Yeah, it's just a linear function that converts
Yeah.
your negative 100 to 100.
It's just
to
a
that.
it's just a mapping function.
Yeah.
Yeah.
The first order.
Yes. So
What's the limit? It says first order.
let's have this.
Like, this just applies to our motors, like, controlling a heading.
Yeah.
But, like, if you wanted to use a PID controller for something else, you'd have to completely write this code again.
No, so not at all.
Application.
So the only thing that will change is your inputs and your outputs. It's just your state variable. Or let's say I want to make a thermostat,
Yeah.
right, where I control the temperature of this room. Well, the input is going to be my temperatures. So instead of heading, and it'll still be a moving average filter, but instead of the values being headings, the values will be temperatures.
Yeah.
And
I mean, like, a lot of this would have to change because you've got, like, 2 variables for your 2 motors and stuff like that.
Yeah. So
Like you really should like separate your classes. Just have like a moving average class, and it's just that's all it is.
you mean this one
Oh, yeah.
that's called a moving average class?
The controller should be just like a PID class that uses a moving average.
That's-
Instead of like having specific things like heading, it should be like more generic.
Okay.
Yeah.
So
And then,
certainly.
and then you can inherit it in that controller class.
Yeah.
Prompt with heading control.
I probably will do that once this is done code. So,
So like
The-
heading control will inherit control.
and you could, but for us, we use this on the boat, so I didn't want to be generic because for variable naming conventions for my projects, I always find it way easier when I know what I'm talking about. So you'll see, like my variable names in some of these places, deck motor command
That's pretty specific.
it's also not my variable name. So that was an inherited one. Heading error is one of my variable names. Get and set timestamp is one of my function names. Clear compass flag is one of my
Like
mine.
those should be in the heading control class, the inherits control.
Yeah, that is where they are.
Yeah.
So if you
But this is a
pay
controller,
attention.
not CVD. Those should be a heading controller, which inherits controller.
heading controller, which inherits controller. Yeah, that's what you can do. You're more than welcome to do that.
And I'm probably low because we need to use this code in the sub.
Okay. I mean, this is also not the code that, yeah, I mean, again, it's not bulletproof.
Yeah.
We will have a code review on this code, and everybody's welcome to come. Maybe not you, Harold, but everybody else is definitely welcome to come. So, no, and I say that, but in all seriousness, it's all valid stuff. Like, that's the point of the code review. It's not the point of what this is now, though.
You're going to use this class for many things. Like, you don't just have heading code, you also have GPS. And other
Yeah.
things that you can control.
Yeah, but again, this isn't a seminar.
Yeah. But also, so we're really not even gonna go with this controller, right? Like,
Yeah.
it's gonna be other
This is an
controllers.
example.
So now we've set this this decimal motor command. So like we said, either your inputs can be your heading, it could be the temperature, it could be the luminosity, it could be anything. And the output can also be something the same. So now this will control a PWM signal output to two different motors. You could also, I guess you would have to change that a little bit, but I don't think that you'd really, if you only had one actuator, like let's say you just want to change a light bulb, you could probably use one all the same because your error is still going to be, the error term will still hold true, whether or not you're using one or two actuators. So, let's see. Now,
Because those actuators are just acting equal and opposite.
Yeah.
So they really are acting the same.
because if you had a light bulb, if you're reading, let's say now I want to control the amount of light in this room, and I have a certain amount of, if there's a certain amount of light in this room and I want to get to a certain spot, I'll have that error and my one light bulb will either increase or decrease depending on what that error is. So whether it's one or two actuators, this will still work. So, okay, now finally, if we're inside the tolerance, we're just going to set the constant motor power. And the last thing that you're going to do is write your motor command, whether it's PWM, whether it's a thermocouple, whether it's an actuator, any type of actuator, this is going to be where it is.
One of those thrusters offline, because the other
Yeah.
one will still be going forward reverse.
Yeah,
So
for sure.
It's basically just acting the same thruster but equal and opposite.
Yeah.
Unless you're adding forward and reverse thrusters.
So the last thing that I have in here is a logging function, where being able to have access to your data after the run is super important so that you can actually map out what your response times were. So I can see over time how my desired heading changed with respect to my actual heading. I can map out what my system response is and see if it is what I think it is. Building up maps, not that we have GPS information in here, but for vehicles, you want to have GPS, you want to have heading, timestamp, and this is actually in the logger function. So I turn it off because this works as is, but you also don't always want to have, you don't want to have a log file every single time you run if you're doing a lot of bench testing. Like you're just running your code. Yeah, so here's a good example, right? Before we go onto the water with the boat, there's a lot of bench testing that we do. And not all of it do I need the data from. So I want to fill up my machine with hundreds of pages of this data that I'm not ever even going to use. So you can either, probably the better thing to do would be to comment it out inside of this code, would really be where to do it. So, let's see. I think I've been over the entire class. We've gone through the whole source code. I was going to try to get into the I and the D term. I'm not going to because it's 8:10. But pretty much where that would go, I'm not going to code it, but I will talk about it because it's important. So what we would have is here, we're just setting this power. We're setting our power directly off of our P term. So what we would probably end up doing is something like in power from P term port and so I would set these equal to this.
I think those should be else too.
Yeah, else.
Yeah. So, yeah, it could be.
get rid of all that shit.
So with this now, so we have just the aspect of our motor power that is coming from the P. So eventually what we're going to have is this motor power is going to be the power from P term port plus power from I term port plus power from D term port. And the same thing with Starbird, except that all of them would be Starbird. So now, how do we actually go about getting what our integral is? So we have what our heading error is. What we would have to do is, where this heading error is set, is in the moving average filter. So, believe, is it? No, pardon me. It is in the controller, which is,
Where's that declared?
it's in the get params is where it's declared. Get params function here. But so, or
No.
pardon me, mode specific setup is where the, oh, heading error
Yeah, where's it
specifically?
declared?
Yeah, that's what I'm looking for.
Should be in the control.h.
Add,
Should be the private control.h.
yeah.
Is it?
I'm looking for where it's initialized.
Oh.
So here we have this set and get heading error. So here we have this return of heading error. So what I would want then is to change this heading error into an array of size 2. So I can have my heading error and I can have my last heading
You
error.
just want, yeah, you want that, you also want an accumulation for the integral. So you want to have an additional to this, the heading error, you want like heading error inch or something like that.
Yeah, so this is actually for the derivative term, is where you would want to have
Well, that's
these
the
two
correct heading
values.
error. You don't, and then you have, you want to have 3 separate ones.
Yeah, no, I know. So for the D term, you're going to have your heading error and you're going to have your previous heading error. For the I term, you would have in controller H, you would have, let's call it down here, you'd have something like float,
Like float previous heading error, and then
accumulated error, something like that.
and then
So what you would do
previous
then
integral.
in this, it would probably be in, let's see.
That's also where you got.
You would have another function inside of here, if you were me, that would just accumulate that error, where every time that there's a while loop, it would call that function in source. So you'd have something like while here would be, PID controller dot accumulate, and it would add that I term. And actually, it would be if you're within your tolerance, if you're within your anti-windup feature tolerance, because you don't want this to be on forever. You only want to be on once you get within a certain boundary once you get within a certain set point from your actual desired heading. So where'd you go? All right, so now if we go back here, let's pretend now that we have that, we have forward heading gain. So you'd have your P heading gain times that the I term, which is going to be that accumulated error. And then you would also have your D term, which is going to be and this is kind of getting just hypothetical now, but so the D term is going to be that your current heading error minus your previous heading error, and the I term is just that accumulated, and you add those together to dictate what your output motor speed is. And that's it. So I've been talking for too long now, so thank you all for coming. Are there any questions? Okay?
No,
No, there's none.
None question.
Then thank you.